Welcome back to Smithy's Learning Room. Today we're having a look at the body in motion, in particular fluid mechanics. Fluid mechanics is the branch of biomechanics that is concerned with properties of gases or liquids. So today we're going to have a look at sports that include swimming, so having a look at the liquid in water, and also sports that look at moving through the air, so aerodynamically, so sports such as cycling. It's important to understand the concept of fluid mechanics because a lot of sports use fluid mechanics, so where the objects or the athlete is moving through the air or through the liquid, say water. And it's really important to understand how our body moves through these properties of gases or liquids so that we can enhance the position of our body or the angle at which we release an object to avoid resistance or drag within these substances. Let's start by having a look at flotation. Now, when we talk about the concept of floating is to be able to maintain a stationary position on the surface of the water or close to the surface of the water. Now, we look at the concept of what we call a buoyant force. So here we have the buoyant forces are forces that are pushing up on the object. So, for example, this is the ball here, or it could be the human body. We have the buoyant force which pushes up. And then obviously we have weight, so gravity, which is pushing down. Everybody has some capacity to float. However, the ability or how well we can float varies from person to person. And our body readily floats on water when the forces created by the body's weight are matched equally or better by the buoyant force of the water. So for an object to be able to float, it needs to be displaced or put in an amount of water that weighs more than the actual object itself. So this would explain why when we're lying in a bathtub, we may not necessarily float, we sink to the bottom because the amount of water obtained in the bathtub is not heavier than our actual body weight. It's also important to understand that the displaced fluid or the water is not just directly underneath, but also around the whole object within the water. When we look at flotation, we also looked at the concept of density, and density is referred to as part of the body or an object in which the mass per unit volume. So when we look at the human body, we don't have density, it's not the same density from head to toe, and you'll see this when you get into the pool. When you try to float on top, sometimes your legs will sink. You see this in females because a lot of their mass or their weight is actually at the bottom of their body, and the bottom half of their body is actually more dense than what the top half of their body is, so it's going to sink a little bit more than what the top half does. Let's have a look at the concept of the centre of buoyancy. And the centre of buoyancy is the centre of gravity of a volume of water displaced by an object when it's immersed in the water. So the centre of gravity for a human body is located at about the waist here. So when we look at the centre of buoyancy, we need to think about the fact that our lungs are almost like an air sac. So obviously the upper half of our body is going to be a little bit more less dense than what the bottom half of our body is. So initially when we try to float on the water, we will float nice and flat. But over time, that angle of flotation, similar to our line of gravity, will change. And you'll notice this when you do it practical in the pool, is that over time, the body will actually start to sink a little bit in the water. And you'll notice that the centre mass will stay the same, but because the dense part of the body down the bottom is actually pulling the body down and allowing the less dense part of the body to float on top of the water. When we look at the centre of buoyancy, it's particularly important for athletes who are doing aquatic events, for example swimmers, to understand where their centre of buoyancy is so that they can correct their stroke or adjust their stroke technique to allow for this to happen. Often you might see athletes train with pull buoys in to try and pull their feet up out of the water, so they're lying on top. And often long distance swimmers, they swim in wetsuits to allow their body to become more buoyant, so they're not having to use as much energy to try and keep their feet above the water to stay floating. So the final concept that we have a look at in fluid motion is fluid resistance, and we look at this concept in relation to water but also in relation to the air. So we have two types of resistance, and we have surface drag and we have profile drag. The best way to look at surface drag is on a swimmer. And surface drag, or skin friction, refers to the thin film of fluid which sort of sticks to the surface area of the body or object through which it is moving. So if, for example, we're looking at the swimmer here who's actually wearing a wetsuit, and we'll talk about this concept in a minute, they've just come out of the water, but if they were in the water, you would see that there'd be this really sort of thin layer around them, which is what we call the surface drag. Now, the concept of this wetsuit, if you have a look at it, it's actually quite smooth, and the technology has been developed to try and minimise that surface drag. And this is where technology in sport comes in, and we have a look at the biomechanics of sport and we say we need to minimise that surface drag so we can make that athlete go faster. And so sporting clothing companies have developed such products such as this wetsuit to try and minimise that surface drag, or those little air bubbles that sort of go over the body as the swimmer's moving through the water. So the other form of fluid resistance is called profile drag, and it's also called pressure drag, and it refers to the drag, or I guess the resistance, created by the shape and size of a body or object. Now, a really good way to have a look at profile drag is among cyclists. So here we have three different types of cyclists. We have our mountain biker, we have our road bike, and we have our time trial. Now, what's really important to have a look at is the positioning of these three bike riders, and you'll notice that they're all relatively aggressive and they're sort of on the attack. But let's have a look at the shape of the bikes and the position of the body in relation to profile drag. So we know that profile drag refers to the drag created by the shape and the size of a body or object. And as they move through the fluids or through air, these athletes want to try and decrease the amount of drag or decrease their size or shape so that they have less resistance against them. So if we start by having a look at the mountain bike, you can see that the profile of the mountain biker is quite wide, and you would see that them coming head on, they're actually causing quite a lot of profile drag there. But if you actually think about the concept of a mountain biker, it's not necessarily, obviously you want to go fast, but not as fast as say a road bike or a time trial bike. Now, if we have a look at the concept of a time trial bike, you'll see the athlete is quite bent over, and you'll also see concepts of the bike. See, the bike frame is quite fat as opposed to the road bike frame is quite narrow. These concepts are all designed to make the bike cut through the air and decrease the profile drag. You'll also notice the shape of the helmet is quite pointy at the back and smooth, so unlike the road helmet and the mountain bike helmet that have quite a few air vents in it, this one is designed to decrease that profile drag. You'll also notice the shape of the bike at the back. It's quite flat, and it's designed to sort of tuck in so that the air goes over the top of it. Again, have a look at the difference between the wheels on the bike. The road bike wheels obviously are a lot shallower as opposed to the time trial bike wheels, which are quite fat. Again, trying to reduce that profile drag to try and get more speed and save energy for the athlete. So if we were going to have a look at what the profile of the airflow actually looks like around the athlete, if we're having a look at the profile of the road cyclist, it would look something like this. It would come in, but then there would be quite a fair bit of drag, especially even on the front wheel, from the cyclist. You'll also notice here that the body is quite wide at the front of the handlebars, which would also create a little bit more drag. So even though it would sort of come in, it would come out a wider distance. If we have a look at the time trial rider, it's more aerodynamic, which means that they're going to have less drag at both ends. Because the hands are close together at the front here, it's going to look more like this. And because of the shape of the helmet and the rear end of the bike, you'll notice that the drag goes like this. By having the fatter wheels, there'll be less turbulence. There'll still be some turbulence off the back, but not as much as a road or a mountain bike. So the important part to realise is the more aerodynamic or the more streamlined the body is or the equipment is that they're using, the less profile drag that they're going to have. So in conclusion, when we try to limit fluid resistance in the form of surface drag and profile drag, we look at technique, tactics, clothing and equipment design to try and reduce these types of drags. And athletes pay quite a lot of money to try and reduce these drags for what they tend to call free speed.